Hi, my name's Steven. I'm here with Rashawn. We are showing you our arithmetic calculator, simple, basic inputs. It's in the RMV7 architecture in D1 SoC for RMV7, so we could have access to LEDs, switches, and push buttons and 7-segmented delays in the IDE. There's an issue previously where it was just essentially like a console, so we needed a bit more interaction ability in order to make the calculation feasible in this environment. Running through the code, you see these addresses for the switches and the button addresses and the hex button addresses. The num1 and num2, the numbers that are going to be stored in the register and had calculations performed on them. This initializes the stack. And then the start function, the main loop is checking key 0. And these are referring to these buttons. Just making sure that whichever button's pressed in the switch, like if I was to do one of these, it would correspond to different numbers that would be referred to in the push button to do calculation on. So I would have 1 checked off, and I would press key 0, and then I would do the second number in the operation, press key 1, and then I would press one of these, and then press key 1, and that would initiate the calculation in this format. You perform the operation. This is checking key 0, storing number 1, to prevent corruption. This is checking if it's pressed, reading switches, and storing numbers, clearing the key towards the end of the function, and exits the function. This stores key 1, stores number 2 actually, checks for the push, pressed, loads the registers, R2, R3, and the base, does the operations, clears the key towards the end, removing it. Checking key 2. This is where the operation is performed, either addition, subtraction, or multiplication. So this register is the base key. Register 0 loads, and then it tests register 1, key 2 pressed, and then it exits key 2. Continues along with a similar string a couple times, and then it does the default addition towards the later part. Do add, do sub, do mul, different store results, and exits key 2. It's all done up here, and updates the display, segment to display the IDE, just so it's actually communicating to the user that something's been happening. And this is just nested calls, but yeah, numbers. Register 3 is extracting digit, R4, R1, R5, or R4, and it moves from registers 0, R2. Then it extracts the digit, R5, move, extracts a loop, R0, R3, and then it's towards the end, clears the display of the hex code. So just quickly compile and run it. Continue. Here we go. And then I was initially press a couple numbers like this, clear it, clear it. So that would be extracted, clear this, try again. Initially, I would need like the architecture behind it to press the switches physically. These are the hex codes, so these numbers are referred to in the registers, using different ways to communicate which number is being performed in for key 0 and key 1, and then it clears it. In this instance, what it's doing is, it's corresponding. So if I was to do 5, it would be 0, 1, 0, 1. So I have to go like this, like 0, 1, 0, 1, and then press the key, and that register that. I would do it again to do it. 0, 1, 0, 1. Press the key and then press key 2, and it would have an output, but it's not entirely functional because it's in this environment, which is only used for really hardware that we don't really have the access to. It's just simulated on this environment. But that's all. Thanks.
This is the code for the Fibonacci sequence in RISC-V that I separated into two files, one for the iterative approach, one for the recursive approach. So the iterative approach, this .data declares a data segment with these variables, one for the input that stores this string, one for the output that stores this string. The space variable stores a space character string. Newsline stores a newsline character in the string. Fib is a array that reserves space for every number that holds space for every number in the Fibonacci sequence. That will add every number in the Fibonacci sequence. Here, .text declares the code segment that stores instructions, and .global main makes the main function global. This part basically prints the input string. It's called here, and environment called here. This part reads the integer input from the user and checks if the input is valid. So executes call to read integer. Here it loads integer t1 equals 0. Here it checks if n is less than 1. And if it is, then it branches to invalid. Here it loads address of the Fibonacci array. Here it handles base cases, so loads register t0 equals 0. So 0 inside fib index 0. Loads register t0 equals 1. Prints result only if n is less than or equal to 1. Loads register t0 equals 1. Stores 1 inside fib index 1. Loads register t0 equals 2. And prints result only if n is less than or equal to 2. Here it iteratively calculates the Fibonacci sequence. Over here, the loop, fib loop, prints result and exits loop only if I is bigger or equal to n. Here it basically calculates fib index I minus 1 plus fib index I minus 2. So calculates byte offset, gets memory address of fib index I, and then loads fib index I minus 1 and I minus 2. Over here adds these two together and stores it in fib result, fib I, stores result in fib I. Over here the counter register t1 goes up by 1 each time and jumps to the start of the loop. In result prints the output string over here, and the loop sets loop counter I to 0, print loop. Over here exits loop if I is bigger or equal to n. Over here shifts logical left, so calculates byte offset and adds it to the address of their fib array, and loads fib to print, prints the number, manages spacing between the numbers. And here, if this is called, t1 goes up by 1 each time and goes to the jumps to the start of the loop, and no space is printed. Over here it basically ends the program. If this is called, the end prints a new line variable and exits the program. And if you run it, so this is the output. For the recursive function, the recursive approach, this is the same except there is no array. The main function, same, it's prints input string, reads the integer, see if the input is invalid, prints output string, and here loads counter I equals 0 and is stored in the register S1 here in the loop. Exits the loop if I is bigger or equal to n, and sets a0 to equal to I, jumps link address to the of the recursive jump and links to the address of the recursive function, loads system call to print integer, and executes the system call to print integer. Here deals with space between the numbers in the output again. Here print space between the numbers. Here again jumps to the target address, the beginning of the loop, and no space is printed. Here in the end, new line at the end of your output is printed and exits the program. Base case returns the base case if n is less than or equal to 1. Over here, loads register t0 equals 1 and branches to base case if n is less than or equal to 1. Here it basically saves the registers, moves stack pointer down 12 bytes, stores return address, stores the current value of n. Basically the first call the recursive function n-1. This is the second call the recursive function n-2. Here adds a result of the first and second call. Here loads the return address, moves stack pointer up 12 bytes and exits and jumps to the return address. Here is handles if invalid user from input and exits the program. And if you run it, you get this out.